1987. Again, our roots here at Hobos initially were in the pressure side as well. So this was a water line in West Texas, 30 miles of pipe, 150 and 175 PSI operating pressures, and this is still in operation today. And I actually talked to the owner of this line about 8-10 years ago, and they said that this particular line is their most favorite piping product of all that they have because of the corrosion resistance and the resistance to the aggressive soils that they have out there in West Texas. So this is our facility today. Not even today, it's been updated. This is a couple years ago, but you're in this facility here, our employee training center. We're going to walk over a bridge that's not in the picture over into the facility. The original plant was here. This is what was built in 1987, and we continue to expand and increase the footprint of our facility. So servicing all of North America out of this facility. And again, we built this originally in 1987, and we continue to grow and increase that footprint. We have over 200 employees today, 13 million linear feet of pipe, all kinds of applications in pressure and gravity, penstocks, force mains, irrigation, and we have some non-circular lines that have been added recently as well. So all of the products are made per ASTM standards. And you're going to see as we go through the facility a variety of manufacturing processes. Pretty much everything that's allowed for ASTM is actually in one way or another a resource that we use here to manufacture piping products. We've expanded the product line here lately with the addition of some manufacturing capabilities, and now we can make both smaller diameter than we used to, as well as higher pressure classes than we used to. So we continue to expand on that, offering now products more tailored to the high pressure water systems. And as you saw, we make manholes, non-circular products, pretty much everything that you can design, fittings of every kind. It's an intersection of two pipes. If you can draw it, we can build it. Some of the main benefits of our product are the long maintenance-free life, the reliable performance. It's really easy to install with the push-together joints. We have a complement of additional joints too that we'll see today, and you'll be able to see some of the newer developments that we have. This is the cross-section. Regardless of which process the product is actually manufactured on, it still follows this same engineering composite design. So we have, whether it's built from the outside to the inside or the inside to the outside, it still follows the same design basis, which is heavily reinforced glass layers toward the outside and toward the inside, and a core in between. So this I-beam structure, as we call it, allows us to build stiffness more rapidly in the product cross-section. And these are the raw materials we use: glass, resin, sand, in a variety of percentages throughout that matrix. We can change the design if we want to change the axial strength of the product, for example, for above ground applications where we need higher tensile strength and the beam strength in the axial direction. We can increase that orientation. If we want to make a higher pressure pipe, we can increase the hoop glass that's provided in the pipe cross section. So all of these raw materials can be varied depending on your particular application. So that's true of the resin systems too. We have mostly polyester systems, but in some instances we move to other resin systems such as vinyl ester systems. If there's petroleum products in the soil, sometimes we go that direction, or very high temperature applications, we sometimes utilize that resin system as well. So again, these are the design standards by which we follow. All of the processes that you're going to see here today are based on the ASTM and AWWA standards, depending on the particular application. So there's the standards address products by the type of application that they're going to be. Is it sanitary sewer, gravity, pressure, potable water, industrial effluents? They all have their own standards to manufacture that product. you, Gabe, I think, to start talking about, testing.
Okay. So the long-term testing standards that we do, there's two main ones. One is going to be strain corrosion, which is what we actually do for gravity systems. For pressure systems, we do ASTM D2992, which is the long-term pressure regression. In essence, it's the same type of test, but just for different applications. What we're doing is we're going to actually take different samples, strain them to different levels. For strain corrosion, we're going to deflect them. And as we have, with a parallel plate test, we deflect them to different levels. We strain them to different levels as well, and they have different fail times, right? We're going to actually plot this in a graph, make a graph, and then that's going to actually give us a predicted life of the pipe. For pressure regression, we're going to actually do something similar, but the samples are going to actually be essentially hydro tested, right? Different pressures, creating again different strains at different failure points. Those failure points are going to then be graphed, and then that graph is going to actually give us a predicted life of the pipe under that certain strain. HOVAS is an ISO 9001, 14001 factory. We do full checks in all raw materials that come in, as well as all products that are tested and finalized. This is a joint that is most commonly used. This is our FWC coupling, and is the envy of the industry. This is a 250 psi pressure class minimum pressure. Sorry, what am I trying to say? 1,000 psi straight alignment tested FWC coupling. It's a push-on coupling with an EPDN gasket. It's very, very easy to assemble, to push them together in the field. So it's really going to be beneficial for you guys, for the contractors. It's something that has been tested over and over again. Every year we do qualifications tests in this joint. And the benefit of this is that you're able to actually cut the pipe anywhere along its length and join it with an FWC coupling and keep going. This is a video of how that happens. As you can see, it's a double fin design. And as the pipe is going in, it's going to actually compress those two fins and create that seal. This video that I'm going to show you, it's a pipe that we tested, 30-inch filament winding SM46 EN200 pipe.
So that pipe was supposed to go to what pressure?
So that pipe was a 200 psi pipe. So factor safety, we're going to talk more about this when we get to the lab, but the burst pressure of that was minimum 600 psi. You can see it far outperformed that requirement. When we get to the laboratory, we'll talk more about how this design basis comes about. That was nearly double the requirement. So John had requested that we were going to do a burst test today, and I would love to do that for you, but as you saw, this happens outside. I don't think we wanted to do that today, but that's why we included this video, so you were able to see actually the burst.
Did we talk about the external pressure test that we've done? The external on the coupling?
We didn't talk about it
Yeah.
in this. Well, a little
Just
bit earlier.
earlier.
A little bit earlier we did. The ASTM standard standards for the joint have internal pressure, angular deflection, shear, and draw. All of those are required for the ASTM standard weeks on minimums. In addition to that, it has a vacuum. The COBAS, because we've been supplying pipe to a lot of really deep tunnel jobs, is what initially started this. We've done external joint testing as well, which is way above what the ASTM standard allows. And we've tested that now. I don't even know the highest they went, 175 or something like that psi external pressure. It's difficult to build test equipment that will seal to this kind of external pressure. It's the only reason we haven't done it higher. So, and there really just aren't applications that have that kind of exterior pressure.
So we also manufacture non-circular pipe. We can do all common shapes, whether it's snag, canal, arch. We can manufacture up to 10-foot sizes, so on the OD, whether it's the width or the height, and then the length, we can actually make 10-foot lengths as well. This pipe can actually be used in slip lining for most shapes, and it's a long-term fully structural design. And what I mean by that is that the design of the minimum thickness is going to ignore the grout, is going to ignore the surrounding host. The final element analysis that determines the thickness works with any shape, any loading condition, and it applies all the in situ loads, whether it's going to actually be the soil load, water load, HS20 load, is going to actually compare to the pipe properties, and factor of safety, and then all that is going to actually give us the design thickness. In general, COBAS pipes can be installed via direct bury, and our pipe happens to be about in general 6 times lighter than the competition minimum, which means that you require much smaller equipment to carry the pipe around and install it. For above ground applications, the saturated casting is a natural UV resistant sand OD. Slip lining, rehabilitating existing sewers. Because of the smoothness factors of our pipe, we generally can actually not only recover the existing flow, but also increase the hydraulic capacity of the line. And everything that we do is 100% leak-free. Microtunneling applications, because of the thickness of the pipe, you can actually require a much smaller bore. It's faster installation because you're able to actually use 20-foot sections instead of 6 or 8. That's something you would actually use with concrete. And it has a non-absorbing OD that is dimensionally consistent, right? Which result in much lower jacking loads to push the pipe. 2-pass tunnel. The pipe is actually very lightweight, so it's very easy to transport to its location. And you also need a much smaller excavation, again, because of the thickness of the pipe. And this was a project that actually John was referencing to a little bit earlier. Do you want to talk a little bit more about it, or did we cover this one pretty well?
Yeah, we just talked about that this is a water conveyance project. It's an aqueduct for San Diego County Water, and this was a design build type of a delivery system. So Michaels was a contractor. They were supposed to do it in 2 years. They managed to do it in basically 1 season. They installed 3,700 feet of pipe in literally 20 days, working days, into this tunnel and grouted in place. So it was very efficient. The lightweight pipe, the weight of the pipe was very important. They could push, I think they pushed 1,500 feet in one session. They had these 10-day shutdowns. In one 10-day shutdown, they did 1,500 feet. And then it was a matter of a couple of days. So it really improves the efficiency. They finished the job essentially a year early. And it's in Trenchless magazines and it's been published. It was a very good project. And there's next phases of the project are going to come out. We'll be also participating in there.
Did I remember correctly, this original schedule was for several different sessions, right, like
Yeah.
shutdowns, right? And they were able to actually like do everything in,
Yeah, so it was supposed to be 6 shutdowns in 2 years.
yeah.
And they did it in 3 shutdowns in 1 season. Basically, it started in October of 22 and finished in January of 23. That's it.
Thanks, Miguel.
So they did make the money. I don't think they gave it back to San Diego County.
This is another example for the city of Phoenix. This one is a 24-inch force main that was running, I think it's 110 PSI pipe that was installed in 2003. And this is actually using axial concrete for the thrust joints. This is an example of where the concrete is being poured in at the elbows. The interesting thing about this one was that the whole line itself was homeless, but whenever it actually got to the structure, the owner had actually some concerns, and he wanted the DIP to actually be, the pipe inside the structure to be DIP. This is what that pipe looked like last year.
20 years. It lasted 20 years and they had to replace all this. The corrosion was just horrible.
Yeah. So going back to horizontal and vertical changes that we can actually make with the joint itself. The table on the left hand side, as you can see, we have the deflected angles on the first column. That's what you can actually achieve. The 3-degree ones is what you can actually achieve with the smaller diameter pipe. And then for our bigger diameter pipes, it's going to be at the bottom. The important thing about this is that we are able to accommodate offsets. We're able to actually do curves, as you can kind of see over here, which tend to be actually very beneficial for pressure systems, right? Because for pressure systems, we're able to use a unrestrained FWC coupling with deflected joints to make changes in alignment. Now talking a little bit about the pressure system design parameters. We have obviously the operating and working pressure. That's typically what we're going to know most about the system. We also have surge system, which is the increasing pressure above operating that happens as a result of a change in velocity. The transient pressure is going to be the operating plus surge. And then the test pressure is going to be what is going to be the field test pressure of the line whenever it's installed. Surge pressure for fiberglass pipe tends to be less than 50% than that of metallic products. And that is because we have a much lower hoop modulus than that of steel or DIP. So whenever you actually compare the effects to the system of what's going on, we have much lower numbers. Should have actually removed that video there. I like the other pull, but this is typically how it's done. You know, it's at a
Cage. You gotta have a cage, yeah.
The design pressure of our pipe is going to be the maximum of the following 3 variables: either the operating pressure, the transient pressure divided by 1.4, or the test pressure divided by 1.5. Okay, that's how we determine what that pipe is really going to be. The pipe burst pressure, which is what you just saw, is going to be a minimum of 4 times that pressure class of the pipe. So, you know, for example, in your project, if we're saying that we're providing a 250 psi pipe, it means that the burst rating of that pipe is going to be above 1,000 psi. Okay. The joint test pressure for your D4161 is going to be 2 times the design pressure of the pipe. So, for this example, it's 500 psi. And then the restrained design pressure, the max peak pressure of the system, the restrained design pressure is going to be the peak pressure of the system times the factor of safety, which is typically 1. Okay. So I say all this because there are a lot of factors of safety already in our pipe and our systems and everything. And you know, I do see sometimes engineers, applying additional factor of safety to the line, and that can get extremely convoluted and you know, too much factor of safety, and makes the system in itself way too expensive. Flexible pipe installation, you have to take into account the surrounding soils during installation. This is really important, right? So this is a typical trench of what you see in this picture. What you're gonna have is a 1.5 times the diameter trench width. That's going to actually go 4 inches below to 6 inches above the pipe. You're typically going to have a trench bedding that is going to be either crushed rock or compacted sand, depending on what is native to your area. And if you're going to actually encounter weaker soils, then an improved installation is going to require lines of cement stabilized sand, a wider trench width, either or, a combination of both. The important thing is that the pipe has enough support to keep it from deflecting. Okay. The restraint joint, this is a restraint joint that we have. It's a key-lock joint restraint system. The coupling itself is actually manufactured as part of the same machine as the pipe. It meets ASTM D4161 gasket sealed joint. It can be used for direct bury, above ground pressure relining. Again, it's also a fast push together type of assembly. It can be used in up to 48 inches diameter and 150 psi pressure class system, which means that it can actually be tested in the field at 225 psi. The restraint joint cannot be cut in the field due to the pipe buildup that we use in the machine. As far as pressure pipe parts and fittings, we have flanges which can be used to connect to valves and other pipe materials. Air release valve structures. This is typically what they could look like with our system. Essentially, it's going to be an encased T with J bolts encased in the concrete itself, and then the structure sitting on top. Valve connections. This can actually be just done inside the structure itself. No concrete encasement is going to be needed. What needs to be done is that the valve needs to be restrained to or anchored to the floor itself, so it doesn't apply any thrust forces to the adjacent pipe. This is probably the most efficient way to actually go and do it. Otherwise, you're going to have to restrain hundreds of feet each side for the pipe itself, and it gets to be very expensive. Ovals can also do tapping sleeves as well. Full circumferential, full gasket, high strength steel sleeve that confirms the OD of the pipe. We can work with the tapping sleeve manufacturer to accomplish this pretty well. Manufacturers that we have worked with before have been JCM Industries, Romac Industries, and Smith Blair. And then if the line is supposed to be hydro tested after it has been installed, you can use something like this. The contractor is able to actually rent this testing equipment from different vendors. This one in particular is from Plugit Products. The only thing that you need to do, of course, is to actually restrain this after it's being pressurized. There's going to actually be a significant amount of thrust force on these, so it's definitely important to actually have a well thought out plan for this. Some ways to actually restrain this can actually be with using sheet piles, existing concrete structures, temporary blocks that are loading the soil, etc. And that's pretty much it. Any questions?
We get a copy of that.
Sure. Okay, well,
I keep hearing the rain. I'm gonna check the weather before we head out on tour. Before we do head out on tour, we will all watch together a safety brief, and then we'll get suited up. We have